Hello and welcome back. So now that we have solved our 2D test case, let's quickly move to the 3D test case. And this will be simply an analogy extension from 2D to 3D. So really we do not need to do a live coding session here. So this will just be an extension of the files which I have already sent. So you will need to go through those files. So I have already done the live coding of 2D, but the files which I have sent are which are in MATLAB, Julia and Python. So they provide a detailed code in which you have a systematic assembly. So in the live coding we just used one file, right, and we just coded everything in that one file. But in the codes which I have provided, you have a detailed breakdown. So you have a driver for running the code, you have a mesh reader, then you have a solver, right, your Laplace solver or your Poisson solver, which actually does the solution. You have a shape function library. In the 2D case, I have given quads as well as triangles kind of shape function libraries, and those are available up to cubics. That means I have given the linear, quadratic and cubic shape functions for all of them. And then you also have an export a file for exporting, right? So this you can read in ParaView. So the solution can be exported to ParaView for better visualization and post-processing. So this is the file format that we'll be using, and you can download it from the GitHub links which were given previously, and that will really allow you to understand what's going on. So I have really just modified the code which I had provided for 2D and I have just extended it to 3D. So this is a simple analogy extension, and that's why we'll not spend too much time, but let's just understand what's happening here. So to understand, we need to solve some test case, right? So I have taken the very simple test case, monopole in an infinite domain. So this is the test case which we started off with. So our initial session was in which we solved a 1D problem in spherical coordinates, which was of course this monopole in infinite domain. So this is simply a Laplace equation solution. So del square phi is equal to 0. This is what we are solving, and we have an inner boundary at radius equal to 1 with phi equal to 50. This is your Dirichlet condition, and you could think of it as a sphere which is releasing heat or mass or creating an electric or magnetic field. So different kind of physics, very simple ones. And then we have an infinite domain, right? And so we truncate this domain at a certain radius. Here we have just picked an arbitrary radius of 12, and we apply the Robin condition, which we also discussed in the previous sessions. At the very beginning, we discussed how this condition comes about and how it is taking into account the effect at infinity. We also solved this in 2D, in which case actually this becomes more like an infinite cylinder, but in case of 3D, we'll be able to actually put an actual sphere in an infinite domain. So we'll be of course solving this in X, Y and Z directions. And I have the analytical solution also here. So in the 1D case, we just plotted it against the analytical solution, our 1D FEM solution. We plotted it against the analytical solution, and we got a really good fit. So let's try out what happens here as well. And so how do we extend our 2D solver to the 3D case? So number one, we are using tetrahedrons instead of triangles. So we have to use the shape functions for tetrahedrons. Our Gauss rule has to change because the 6-point Gauss rule for triangles will not be applicable here. So we'll have to use a 3D Gauss rule, right? So that will be another change. Then your boundaries will change. Your boundaries used to be lines in case of 2D, right? They were simply lines, right? These kind of line elements. So now instead of line elements, we'll just have triangular elements. So we'll only be considering tetrahedrons here. We'll not go for bricks. And in the actual demo, I'll only be showing linears. So these will simply be linear triangles. And so our Robin boundary condition, which we want to evaluate, we'll have to basically take a boundary integral on a triangle. And for doing that, we need again the Gauss rule, the 6-point Gauss rule on the triangle once again. So the same 2D analogy which we applied inside the triangular mesh, now we just apply it on the triangular mesh on the surface, right? The Dirichlet condition imposition at the inner boundaries, that's just a strong imposition, so that will really be very similar. So that is the analogy, and again, the other important analogy which we must talk about is the Jacobian. So we talked about isoparametric mapping, in which we mapped this 2D triangle to this 2D master triangle, and we also talked about how these blue guys, these blue derivatives, which are your master, your shape function derivatives in your master elements in the psi and eta directions, because these were 2D, so these were psi and eta directions. So they can be mapped to the physical, the derivatives on the physical element by using this kind of a transformation. And we talked about the Jacobian J, this J matrix, which is the Jacobian of transformation, and we also talked about how we calculate this, and then we simply have to invert this matrix to get your derivatives in your physical element. And we also talked about how to do the mesh quality analysis by using the Jacobian of transformation, and we also talked about how it's scaling the area. So really that analogy extends here, and the Jacobian really, instead of scaling the area, now it will scale the volumes. So it will be like it will represent the ratio between your physical and your master element volumes. And your Jacobian, instead of being 2 by 2, here it will be 3 by 3, because here we have x, y, z directions, and we'll represent our master element in 3 directions, which we represent as psi, eta, and zeta. So that's really the analogy, and now let's just quickly go to the code and see how this extends to the code.